Thank you, Duncan, for the invitation to this talk. My name is Karin Fornazier. I am a research associate at FUSP Brazil. I will present some results that are in one paper that we published last year, that is Foreground Removal and Bispectrum Analysis in Bingo. And also I will present some preliminary results related to the PhD thesis, Alessandro's PhD thesis, related to the blind methods applied to the foreground in Bingo. All this work were done when I was as a postdoc in UCL, supervised by Professor Felipe Abdala. I will try to cover a lot of things, but mainly will be the sky model used for the simulation, the Bingo sky coverage, which means the mask that we used, the white noise that we include in the simulation is good to emphasize in this second slide that we are not included the 1/f, which is simulation is a little bit more simple. We make then the analysis of this foreground removal methodology, in which we will present all the PhD results that Alessandra got in the Genuk GEM-CA and FAST-ICA. Then I will present the bispectrum that we used here as a tool for cross-check this foreground removal, the other preliminary results, the conclusion, and if I have time, I will show the other projects that we are in developing here. So as Alessandra talked yesterday, the Bingo aim is to determine 21 centimeters for identification that BAO. Here in my left side, I put all the papers that Bingo project published last year, and I highlight in light pink 2 papers that are related to sky simulation and foreground removal. However, in this talk, I will give more focus in 2 papers, Fornazier et al. And Marins et al. That is in preparation. We basically have a sky simulation, which is completed with foregrounds, 21 centimeters white noise, a Bingo mask sky coverage. Then we have results concerned to blind methods, which means Genuk, FAST-ICA and GEM-CA, and also results concerning to bispectrum. Regarding here that this bispectrum model also were the aim of one of our students, Jordani Vieira, in his master dissertation. As you saw in yesterday presentations from Alessandro, our 21 cosmological maps are made by the temperature fluctuations and H1 centimeters. This map, for the construction of this map, we use 2 main codes, Flask and UCLCL. It's important to mention that bispectrum is a tool that not only is used to cross-check the foreground removal, it's also a tool that we used to check the non-Gaussianities, the presence of non-Gaussianities. That's the reason we use Flask. Flask is a code that gives us the option to work with, to include a non-Gaussian behavior in a Gaussian CL provided by the UCLCL. In this sense, I have a control of my input map, my simulation map, so I know what type of non-Gaussianity I have, and so if my bispectrum model is working properly, I will recover this non-Gaussian behavior. In this sense, UCLCL is the code that provides us the CLs, and these CLs came from different types of cosmological models. For this simulation, we just use a very conservative lambda CDM model. It's also important to notice here that in all types and all maps that you will see here and use it in our analysis, they were generated with different seed number. Sky simulation, we use the PSM, which is the Planck sky model. For the in our, I don't know how to change this here. But for our components that the PSM can give the 10 options for simulation components. In bingo case, we choose 5: AMA, CMB, free, FRPS, and synchrotron. It's important to mention that we use the celestial coordinates. The N side in the entire simulation was with 256, 30 channels, and in which the frequency range is covered by 960 to 1,290 megahertz. It's also good to mention that both N side and this number of channels can change for the next years, since the instrumental investigation is improving. We also included a beam. Here is the Gaussian beam, but however, the beam that we use here is a very simple one. It's not that more deep and complete that Alessandro showed in his talk yesterday. Also, we didn't include the thermal dust emission, since this one is very subdominant in our bingo frequency range. And for the foreground maps, all the foreground maps were generated with the same seed number. So 21 centimeters difference in the number, foreground, same seed number. Here I go just through very quickly, because this is just a small issues regarding to the AMA, CMB, and all the components, but all of this you can find in this reference. And what is more important here is to emphasize that for synchrotron simulation, we did not include any effect related to polarized synchrotron emission. This is just because an instrumental issue that is discretized and a little bit more detailed in the Abdallah et al. 2021. I have now my 21 centimeters. I have my foreground map, so I must to apply a bingo mask. Here we used a bingo mask in which covered the region between minus 22.5 and minus 7.5. Again, nowadays this bingo mask is a little bit different, since a lot of instrumental issues has been increased. So the apodization mask is around 5%. The smoothen here applied is 10-degree Gaussian beam. The brightness, we have that 10% were set it to 0, and 30% were attenuated with a cosine apodization function. Here I have the results with the angular power spectrum. As you can see, the 21 centimeters, all this power spectrum is concerned with after I applied the mask. I mean, it is not full sky, it's a masked one. And if you look at our dashed red line, this one is our 21 centimeters. Then you can see that CMB and AMA is probably the components near the same magnitude order. The white noise used in bingo in this simulation was developed by Jacques Delabrie. And for this one, we used the horn configuration described yesterday by Alessandro Marins as a double rectangular. Also, we included here and considered the 28 horns. It's important to mention that we made an assumption here in this simulation where the observed time is uniformly spread across the bingo survey area, which is in opposite what is described in Abdallah et al. 2021, because there is a non-uniformity of the coverage concerned with the layout of the horns and focal plane. The more things related to this white noise, it's important to mention that the temperature of the system is considered around 10 Kelvin, that the total noise per pixel here is described by the sigma pix equation, in which the F sky considered is around 15%. Here is important to mention that we add to this RMS image that you are seeing in my left side, and the left side is added to our Gaussian maps. It's these Gaussian maps, all of these were generated in inside 512. These Gaussian maps were generated in a different seed number, and then we downgraded it to the inside 256 in order to make it more reasonable for the analysis. I have now my entire sky seen by the bingo. In this sense, now I will start the foreground removal, and we used here 3 blind methods: fast ICA, GMCA, and GNU, and 2 different approaches. The first approach was performed by Alessandro Marins, in which he used 400 cubes. Cubes means here 1 cube is equal the third maps related to the third channels. So we generate 400 cubes with the total foregrounds, which means components, 21 centimeters, white noise, 400 cubes just with the information with white noise, 400 cubes with the information with 21 centimeters only, and 400 cubes with 21 centimeters plus white noise, because this 21 centimeters plus white noise, we use it as a prior in most of the blind methods. The second approach here is performed and explained in Fornazier et al. This one we just used 100 cubes, same type of simulation. However, we just used the GNU, and then our aim here was the bispectrum. The noise bias procedure used it is the same in Marins et al. And in Fornazier et al. Here you have the CLBM. BM means blind method. So here in my CLBM there means that my CL obtained after the debias procedure. This one I got from the CLBM1, which means my first output map, over the average, over the S head. This S head is my CL. The average between all my output blind methods maps over the 21 plus noise maps. Then I subtracted this ratio from the average of noise. This is the noise procedure that we performed. Alessandro, he included statistical tools related to jackknife variance and chi-squared and pi values. The chi-square here, we show the preliminary results for the fast ICA. Here we have for results related to the number of realizations, which means 400, 200, 100, 50, and 25. The same for JMCA. The jackknife variance corresponds here to the error bar. Again, we have here the result when you have the GNU, the same procedure and the same comparison with the different numbers of realizations. The axes here are concerned to each channel in the frequency channel. The picture below, we present the chi-square for the GMCA, fast ICN, and GNU, where you can see that the chi-square didn't show any huge difference between them. The same we can see here the comparison in the chi-square effective one when we compare the JMCA, our blue line, the fast ICA, dashed yellow one, and GNU, the black solid one. When you make the comparison of this chi-square effective, you see that GMCA and FSA are almost equal, and GNU sometimes for different channels has a little bit different behavior. However, when we compare the chi-square overall, we see that from these 3 different methods, there is no huge difference in the results. Of course, we have to keep in mind that one, we didn't include 1/f noise. Second, the beam here is a very naive one. It's not a instrumental and a real one. So of course we will find differences, and when we include this instrumental information, for sure this behavior will be improved, or sometimes they could be different between the three methods. What we want to emphasize here is that for the simple and naive simulations, the three methods are equal for this case. Here I present the results when we are using the same noise device. However, here I just use 100 cubes and GNUC results. What is more important here to emphasize is that GNUC has a variable that is called MAIC. This MAIC is a foreground dimension M, which minimizes the archaic criterion. This criterion is described very well in Oliveira et al. 2016. What we did here is we know from this MAIC, I mean this archaic criterion, gave to the GNUC the best optimization. We intended to use the Bispectrum as a foreground removal project. In this sense, we made GNUC we decreased this archaic criterion, and we made the GNUC gave to us three different outputs. A suboptimal one, which means that MAIC criterion is -1. The good one, which means the MIC itself, and an overestimated one, that is the MIC criterion +1. Here I have the residuals for each component for two different aspects, with noise and without noise. So in the left panel, you have the no noise residuals for the best choice in the archaic criterion in GNUC, and white noise residuals on right side. Here you have the genomic view for each residual component, and my first line, I just showed the no noise, and in the second line, we showed the component added with the white noise. This shows how the white noise can contaminate the residuals and the component. Here I present the suboptimal criterion in the GNUC. Regarding here that this suboptimal is forced by hand because we want to compare these results with the bispectrum model that I will describe further. So here I have the suboptimal, I mean the underestimated GNUC output, in which you can compare. Below, I reproduce the white noise and the no noise for the best choice in GNUC, and you can see that, for instance, that CMB residuals presents a different behavior. So the presence of white noise and the presence of this underestimate GNUC process can give problems, of course, to the results in the residuals. Same here in mnemonic view, but here for the underestimate case in GNUC. Also here I input the overestimated situation for the output in GNUC. Again, you can see the influence of these results mainly in the white noise behavior. And again, the AMA, CMB, FFI residuals, and the comparison with no noise and white noise. When I'm talking about bispectrum, is the idea, first of all, is the study of non-Gaussianities that could be present and could be imprinted in 21 centimeters map. And mainly that it could be also present in this case because we forced this presence because we included that log normal behavior in the flask maps, in the 21 centimeters maps. So why we are trying to use bispectrum? Because bispectrum is a three-correlation function that gives us the high-order statistics to characterize this non-Gaussian behavior. In this sense, and in this talk, I want to really to emphasize that bispectrum here is used as a double check first for a cleaning procedure and not to get cosmological information. To get formological information and either for FNL and GNL is our future steps. Here we just use it as a double check. Bispectrum in 21 centimeters analysis is not something ineditus, and I mean, you can find it in the literature. A great number of authors like to use bispectrum as a tool for 21 centimeters. And here we used Smith and Zaldarriaga in order to create our Gaunt equation and our BL function, and Regan and Scheller in order to create our contour map. So here I just put the Gaunt equation. This is the G equation that you see in your left side. This G equation is the responsible for the great time consuming and great time computing consuming for the bispectrum analysis. Nowadays, our student, Giordano Vieira, he reduced this. For instance, if you want to calculate bispectrum for isosceles case, which means L1 plus L2 equal 100 or 200, this code in Python took more than 30 days. Nowadays, since we changed it for C++ code, now it's just taking some minutes. In this sense, our results, our future results could be better, and we can investigate it deeply more. Here is also good to emphasize again that there is several configurations to estimate non-Gaussian. We choose the equisize one, which means equilateral triangle, and you see the geometrical view of this is a equilateral triangle, and we use the combination that the sum of the sides of this triangle could be equal to 30 or equal to 60. These numbers are limited by the time consuming, computing consuming related to the code that was written in Python. Here is the first results using bispectrum. First line, I have my total input, which means foreground 21 centimeters and white noise. So, and the columns are related to each channel. Here I put just channel 10, 15, and 20. The second line is 21 centimeters plus white noise that is also used in prior for the blind methods. And the last line, I just show the white noise presence. I mean, the results, my BL equation when I use as input white noise maps, 20 centimeters plus white noise map, and the total input maps, I mean, foregrounds, 21 centimeters, and white noise. I circulated in red a pixel in a position -5 and 5. Please keep in mind this position, because when we plotted in the contour plot in an equisize triangle, the output from GNUC, we see that bispectrum can be sensitive to foreground removal. For instance, my first line is the results from the GNUC when I underestimate GNUC, when I force GNUC not be in the optimum in the optimum situation. And the second line is when genuque is the good one. As you can see, bispectrum is sensitive for the presence of some residual from the foregrounds that you can find when the genuque is suboptimal, and you didn't find when the genuque is in a good performance. Here I just put the comparison between when you have in the upper slide, in the upper plot, you have the underestimated genuque output calculated by the bispectrum function, and the blue is when we considered everything equal, the sum between sides equals 60 and yellow equal 30. And there is the second plot is when you are using the genuque optimum criterion. So you can see the difference, and you can see how the equation how bispectrum function can be sensitive to it. Here again, just more results concerned to the bispectrum residuals calculation. I know that I am almost in time, so my conclusions are here. For the Marins et al. Preliminary results, we have that 3 blind methods for this type of conditions and simulations. We have similar results. Regarding that, we didn't include 1/f, so which must be included if you want to have more precise results. Bingo beam must be impacting these results, so we must be tested. And we must test this map and simulations in a complete simulation with a non-blind method such as a commander. For bispectrum model, we realize that our model can detect the presence of non-Gaussian information, regarding that this non-Gaussian is also present in residuals, because if there is no Gaussian information, we will have a BL completely equal 0. The model also can be a tool for cross-checking for the foreground removal. The time computing, we are almost to solve this issue, and we must simulate this for L and N greater than 60, and we should test not only with blind but also with non-blind method and with different experiments in order to check and cross-validate this model. And this is just a propaganda for which group are also involved. We are leading multi-wavelength data analysis, which means that we are cross-checking and cross data from spectroscopy, photometric, and radio data. We are using machine learning for code for this. We are investigating a mask used for 3 different experiments like SDSS, DES, and bingo issues. We have a power spectrum and pseudo power spectrum studies and working. We have a likelihood feed, and the aim of this work is massive neutrinos detection, in which Gabriel is helping me, and Gabriel will present something tomorrow related to the Cosmoglobe simulations. So you are welcome to join us, and thank you so much for your attention.